Hey everyone, today we're going to be talking about teleportation movement in VR in Unity. So a little while ago I made a video about how to create a basic bare bones XR rig in Unity using the XR Interaction Toolkit. And this video is going to kind of take off from there because I got a few comments asking for some different things, and I thought, well, might as well make a couple more videos, maybe turn it into a series, who knows. But anyways, yes, we're going to be picking up from there. So if you haven't seen that video yet and don't have a basic XR rig in your project, maybe go ahead and watch that video. I'll have it linked. But anyways, to kind of go over what we're going to be doing here, teleportation. So we're going to include anchor teleportation, so that is teleporting to specific points, as well as free teleportation, so being able to teleport anywhere on sort of a ground surface, as well as we're going to be doing the straight raycasting, as well as the projectile style curved raycasting, which actually is going to be, that's going to be in a separate video. That's going to kind of continue on from this video. I didn't want this video to get too long, so we'll just do that separately. It's going to be quite involved because it requires a bit of math and a little bit of extra setup and stuff. So anyways, if that is something that you want, we'll very easily just fit that into the system that we have here. I will also say that the XR Interaction Toolkit starter assets actually has a pretty good teleportation system already. Even if I just go to an object here and type XR, you can see that there's a whole bunch of stuff in here already, like the ray interactor, and then there's the interactor line visual. That stuff is all there for the teleportation and UI interaction and stuff like that. And it is pretty robust. So if you want something that just works and has a ton of features, maybe go ahead and use that. Again, with the starter assets, it's kind of all set up for you too. Keep that in mind. But if what your goal is here is to either have something that's a little bit stripped back, a little bit easier to understand, maybe a bit easier to modify, or you're just here to kind of learn how these systems kind of work, then this is the video for you. Last disclaimer, this is a pretty coding heavy video, and it's not an introduction to C# or Unity. So if you don't know, say, for example, what physics.raycast is, or what a ternary operator is, which is something that I'm going to be using quite a bit in this video, then maybe go ahead, read up on that, and then come back once you're a little bit more familiar with how we code in Unity. So anyways, let's get started. First thing, we're going to create a script, and I'm going to call it player teleport. Open up Visual Studio with that. And since we're doing a few things, I'm going to do this all in one component. You could break this up into different components, like have the actual raycasting be a separate component than the teleportation handler and stuff like that. But just for the simplicity of learning, I'm going to put it all in one thing. So we're going to be doing a few different things. So first thing I'll do actually is create some enums here, which is going to be the teleport type. So I said that we're going to be doing the free teleport as well as the anchor teleport. So this is just going to allow us to switch in between those two in our inspector. We're also going to have another enum here, which is going to be the cast type. So that's going to be what type of raycast we're going to be doing. I need to specify that as an enum. I'm going to write this out, but again, we're not going to do the projectile math here in this video. It'll be in an accompanying video, but I will still list it out here so that we have, and we can refer to it. So linear and projectile. All right. Now let's, I'm going to write out some serialized fields that we're going to need to have. So I like to organize these in my inspector. So there's actually a tag here called header, which you can use to add like headers and split up different serialized fields so that they can be easily categorized and not just one big blob. So I'm going to create a general header here, and we're going to have a serialized field, and we're going to do that teleport type. I use the m_ camel case coding convention. You can use whatever coding convention you want. Just so you know why I'm putting this m_ in front if that's not something that you're used to seeing. So we're going to have our teleport type, which I think by default will set to the free type. Then we're going to go and also do the cast type. Cast type equals, we're going to start with linear because we're going to do the projectile in a separate video. Next, we're going to need a few layer masks, which are basically going to help us when we do our raycast and stuff, so that things don't get too computationally heavy. We're going to have basically the ability to select different layers that we actually want to check physics on. So serialized field layer mask. One is going to be the all collision all collision mask, which I'm going to set to 0, which is the equivalent of none. I'll show you what these look like in the inspector if you haven't seen them before as well, once we're done here. So we're going to need another layer mask, which is going to be valid surface mask. What this is for is valid surface is going to be when we're using the free teleportation, and this can be any surface that is valid for us to teleport on. The reason why we need this separated from the all collision mask is because we still want to detect whether or not that surface is valid and place our little we'll have like some kind of visual indicator that'll show where we're trying to aim. So we want one to actually do that, and that's going to be the actual calculation there, but then we also want another one to see, hey, are we actually allowed to teleport here? So we're going to do one for, so this is for the free, as well as we're going to have another one here for anchor specific, because those should be on different layers. All right, last couple things in general. When we're doing the free collision, we're going to need sort of a way to determine if a surface is too steep for us to teleport to. So we just need an angle for that. So serialized field float. And I'm just going to do a max free slope angle, which I will set to 45 degrees. Now, the last two things here are two different colors. Now you can do two different shaders, you can do whatever to make it look fancy, but just for demonstration here, I'm just going to be switching colors whether or not we can teleport or not. So having a valid teleportation target or an invalid. So color is going to be invalid color, which I will right away set to color.red. And then we'll have a valid one, which I will set to green, just to make it super easy for us to see what's going on. Okay, next thing we're gonna do here, we're gonna create another header for our inputs. In this case, I think we will only have one input, but I'm gonna do serialized field input action reference. You can put the input in here directly, input action in here directly if you want. I have a video on how I use the new input system, so I'll link that as well if you want to go check that out. I tend to use the input action references and then actually create these action maps separately and stuff like that. Anyways, I'll just call this input. Actually, no, let's call it move axis, just in case we want to add some other inputs later, something that's a little bit more descriptive. And then I need so my plan here with the input is I'm going to use the forward stick. So we're actually going to be getting the whole thumbstick as a vector 2. So I'm going to need sort of a threshold for when we're going to be triggering that. So let's do a float m input trigger value, which I'll set to 0.8 is pretty high up there. So we'll do that one for now. Now we need a header. We do another section for linear casting, and we only need serialized field, not header. We only need one property here, which is just the max cast distance, which I'm going to set to 10. This needs to be a float. This is just basically going to be a limit on how far the raycast is going to be. We'll have another header here that we'll insert later for the projectile raycast values when we get around to it. And then just another header for, I like to put at the bottom all my references that I need. So what we're going to end up needing is, in the inspector anyway, is a cast transform. So basically, where are we shooting our raycast out from? So we need our cast transform, and then we need another transform, which is going to be the, what I want to do is there's going to be a line that we're going to draw, but then there's also going to be some other object that's going to be at the collision location. I'm going to use a sphere, but you could use like some kind of a disc or some fancy looking thing that can honestly just be any object that you have that you can just drag into here. So we're going to call this the target indicator transform. All right, last couple references. These ones don't need to be serialized. We're gonna need the camera. I like to store the camera always instead of always getting camera.main, because that does like a string lookup every single time you get it. So we're gonna do it once. Line renderer, which is going to be which is going to be actually a component on our thing. So I'm actually going to go ahead and do this, require component type of, and then we're going to switch out rigid body for line renderer. What this does is anytime we add this component to a game object, because it has this require component type of line renderer, it will also add a line renderer at the same time. It also won't let you get rid of the line renderer without getting rid of player teleport or whatever your component is first. So that's just a good way of making sure that you always have that and that it's never just kind of not there or forgotten. And then last, we're going to need the renderer of the target indicator. I spelled indicator wrong here, didn't I? Indicator renderer, because we're going to need to change the color value on that as well. Unless you don't want to change the color on it and you want to do something else with it, that's totally fine as well. Now, there are two more values that I need here, and this is just kind of thinking ahead as to how we're going to be doing this. We basically need to tell our update loop whether we need to show and do the math for the calculation. So basically whether or not our input is down or not. We also need to trigger turning on and off our visuals. So that's kind of why this is important. And sorry, this is a Boolean. That's going to be set to false by default. And then float max slope is going to be, we're going to be using something called a dot product for checking our terrain angle for how steep it is. We'll get into that in a second, but we're just going to need a value to store that because we need the result of the dot product, which is going to be different than the actual angle that we specified up here. So that's I'll just set it to 0 for now, because that's going to be set right away. Before we get going, actually, I'll show you the I'll just show you what the layer masks look like, just in case you haven't seen those before. Let's go ahead and drop this on our XR origin, just on the default one here. You see it added the line renderer by default here. But anyways, so these are the this is why I use enums a lot. We have these drop downs for the free and the teleport type and the cast type. And then our collision masks here, we can set these to any number of, or a combination of these, and obviously everything or nothing are shortcuts for deselecting and selecting everything here. So these are very handy for us being able to set, and that's these layers that are up here. So like this cube, for example, could be on the water or whatever. But anyways, jumping back in, we're gonna go ahead and start things off with a start method, which you may already have, but I'm actually just going to go ahead and write some error checking stuff that I like to add. You can copy this after the fact, but I'm going to speed up the video for you guys. All right, so one thing I always like to do is put in a bunch of errors and warnings to let me know if I haven't set up the component properly. So in this case, I've got, we really need the cast transform. Actually, I should also have one here for the target indicator as well. Let me go ahead and do that. All right, so these two here, make sure that we have these two references here. So what that means is I'm not just using debug.log, I'm using debug.log error and debug.log warning to give me these, make sure these things pop out to me or to anyone else who's using this component after me on the team. So this basically just lets me know that I put the name of the component type in here. Sometimes I'll put the actual object name if it's something that like there's multiple of them. But anyways, we're basically saying that these haven't been assigned in the inspector. So if you see like, oh, a whole bunch of null reference exceptions and stuff, and then you scroll to the top and see this, you know exactly why. The other thing here is we're checking, this is the reason why I set these layer masks all to 0, is because 0 is none, which means that none of the layers are set. So in this case, we're just giving ourselves a warning saying that each of these layer masks is set to none, because that's probably going to be useless, because if it's set to none, we're not going to be doing any collision checks. It doesn't break the component. That's why it's a warning and not an error, but it is something that we're probably going to want to deal with. Also just checking to make sure that we're doing free teleportation for the surface mask, and we're anchor for the valid anchor mask as well, just so that we're not getting extra warnings when they're not necessary. Okay, so next thing we're going to talk about actually is just that dot product thing. I'm actually going to hop over here and to write down some stuff here and show you how we're going to be calculating the surface here. All right, so how are we going to calculate the steepness of a surface? Well, let's just say we have a main ground here, and then we have a surface at this angle. Let's make it a little more straight here. A surface at that angle and a surface at this angle here. We're going to say that this angle here is too steep, but this angle here is perfectly fine. This is something around, say 30 degrees, this is something around 60 degrees. No, it's not perfect, but we'll just assume that. But when we do a raycast onto a particular object, there are a few things that we get from like the hit info that when there's a resulting raycast. One is the actual point in which that we're having our actual raycast. The other one is what's called a normal, which is a unit vector, which means it has a magnitude of 1 that goes perpendicular to the plane in which the collision was happening. So it just basically shoots up directly away from that. And we can end up using that to help us figure out our steepness here. Now, what is a dot product? So a dot product is a type of multiplication that we do between two vectors. And it actually gives us, it's two vectors, but the result is a scalar. So there's no directionality to this. An easy way to kind of see this is if we have vector A here, we denote vectors with this little arrow here. And then we have vector B here. So these are both kind of going out and they have an angle, right? This is B. If we go A dot product B, that will give us the magnitude of this section here. So basically how much of B overlaps on A. So we'll call this just like C lowercase, right? So that's a resulting value. So what we can do with that is if we compare this vector here, our resulting normal, to our up vector here, what that will do is tell us if it's perfectly up, we'll basically get a value of 1. If it's perfectly perpendicular, we'll get a value of 0. And if it was to go the other direction, like we were actually, the face was facing downward, we would actually get a -1 value here. Because specifically these values are 1, 0, -1, because these are unit vectors. They have a magnitude of 1. So what does that mean? That means that we can basically, if we know what, say, our maximum value is, so if it was 45 degrees, what does this value look like here at 45 degrees? We can check if it's above that value or below that value. And this is a really quick way of telling the direction of something relative to another direction without doing a whole bunch of raycasting. So there are a few formulas. So if we actually look at what is the formula for dot product, there's a couple of them. One is the dot product is going to be AX BX plus AY BY, and then if you have 3 in your vector, it would also be AZ BZ. That's going to be the classic dot product formula. But we actually have another one, and that is the magnitude of A times the magnitude of B is multiplied by cosine of theta. So if you have theta, you can still get the dot product using this formula. And because we know that we're using unit vectors here, these are magnitudes of 1, so that we're just multiplying 1. So that gives us just cos theta for the value of whatever that value is. Now we do need to think that this is in radians, not degrees. So we do need to make sure of that. Well, particularly in Unity's API with the mathf library, it's going to be radians. So we're just going to need to keep that in mind. So that's that value that I was talking about before, the what was it called? The max slope, we're going to basically just do cosine theta to get this value so that we can compare against it. And when it comes to dot product, it can be a bit of a tricky concept. So I will link an article on explaining dot product in the description as well, if you want to dig deeper into that. Let's hop back over to Unity here, and going back into Visual Studio, we're going to calculate that max slope value that we've got here. So that's going to be max slope equals just math f. Oh, I'm not in the start method. Hang on. M max slope is going to be math f dot cosine of degrees to radian. Sure, we'll take that, but not delta time. Visual Studio. Max, it's the max free slope angle. So that's our serialized value. And so we're just storing this to make sure that we have it. And then we're not doing, because cosine can be pretty expensive if you're doing it every frame. So we just want to store this beforehand so that we don't have to calculate it again. The last thing here is I'm just going to create a little method here for set visuals, or let's say set is aiming, because we'll set the other thing as well. We'll set to, and then so aiming is going to be set to that, and as well as we're going to have the line renderer enabled is also going to be set to that, and then the, what was that called, the target indicator. I guess this works as well, but I kind of want this to look, I'll use set to just so it looks cleaner. All right, and so we're gonna set that to false. So this basically goes ahead and just, set active, and that's, there we go. Almost. We need to set the game object test. All right, so that's basically just going to make sure that we this stuff is all turned off, so it's not hanging around in our scene when we're not pressing our button. All right, now we're going to get into our big hefty update loop. So first thing we're going to do is we're going to get our axis here. So the way that we're going to get this is, again, this input action reference here, it's going to be a vector 2. So, but the idea here is that you're going to press up on the thumbstick, and then that will bring up your indicator where you can aim. And then when you release that, that's when we're going to do the actual teleport, if we have a valid surface. So input axis. So since we're going up, that's going to be the Y value there. So it's going to be our M move axis dot action dot read value. And again, that's going to be vector 2. And then we're going to get just the Y value of that. We don't need to store the X value right now. So, and now we're going to trigger if we are turning on these this set aiming stuff and beginning our actual logic here. So so this is the value that we stored up here, just so that we're calculating onset and offset of this. So if we're not already aiming and our input axis is greater than input trigger value, so we're moving up past the trigger point, which is I think 0.8, because it's a 1 to -1 scale there, then we're gonna do the set is aiming to true. So that's going to bring up everything that we need visually, as well as now we're going to say, so after this point, if this is false, so we're not aiming, we might as well just get out of here, because we don't need to do anything else in this update loop if we're not trying to aim. So now we actually do the raycast. So here's what we're going to do. We're going to need a couple things first, and that is we're going to create another enum. This one is just going to be private. We don't need this to be public, but this is going to be called hit state. And so when we do a raycast, we're actually going to have 3 different states that we want to check. One is a miss, so that means we didn't hit any geometry whatsoever. Then there's going to be the hit state, so we did hit something. And then there's going to be a valid surface. We'll call it valid target to be more generalized because we're talking about surface and anchor. So we'll say valid target to encapsulate kind of both of those ideas. And this is just going to be that it's either the anchor or it's a floor or something that we're allowed to teleport on. So first thing we're going to need is an instance of that. So that's called hit state. So we're going to call that, and we're going to set that to miss just by default. Next, we're going to need all the Raycast, physics.raycast library of functions in Unity return something called the Raycast hit. So because I'm going to plan on using a switched case here, so that's why this stuff needs to be out here. So I'm going to call this hit info, and we're just going to set that to default. And now we're going to do our actual raycast, and I'm going to put a switch statement in here because we need to have both the linear raycast as well as the projectile raycast, which we'll be doing later. So this is going to be the cast type, not transform. And then first case is cast type dot linear. I'll just put the break in here already. Cast case cast type dot projectile break in, and then default case. So whenever I use a switch statement on enums, I always like to do a default with a dedebug.log error that says player teleport. Let's actually put it as like it's like the function's written. And that's going to be unimplemented cast type enum. Because we should never hit this state ever, it's good to put this in there just in case we do end up adding, say, like you want a Bezier curve or something like that as well, and you end up adding another enum here. It's nice to have this little error so that you know that you didn't implement it and you kind of know where to start looking if things aren't working. But now I'm going to create a couple functions that we're going to end up using here, which is going to be private pool linear cast, which is going to have an out raycast hit info. So we have that one, and I'm going to go ahead and create, let's return false just so that we get rid of that error. And then we're going to have the projectile cast, which will also return false, as well as, sorry, hit info needs to be default as well, because we have that out statement there, right? Again, we're not going to be implementing this one in this video. It'll be in another video, but I'm just going to have it here just so that it is in the code here. So now next what we're going to do is we're going to do a raycast inside of these. This function is going to do the raycast as well as it's also going to set up our line visual so that it's either a straight line or like a projectile line. The Boolean is going to be whether or not there was a hit at all, and then the raycast info is going to contain that raycast hit info that is returned from the actual raycast as well. So if that's the case, I'm going to create an if here and say if linear cast, and we're going to do out hit info, which is this guy up here. Then we're going to set the hit state to hit state dot hit. So that means we hit something. Otherwise, it's just going to stay as a miss. And then we can do the same thing. Oh, that was in projectile. Anyways, let's copy that up here and change this to projectile. So the switch case is basically just getting whichever cast type we're doing and then consolidating that info into these two here. Now that we've got, so we'll do the raycast. Actually, let's do the raycast now. So the raycast is pretty straightforward for linear casts. So bool has hit is going to equal the physics. Hang on, if I can type. Dot raycast, and then we're going to get basically the cast transform. So this is going to be somewhere on your hand. Cast transform dot position, And then we're also going to get so the next is like, which direction are we casting it out of? And we're just going to do the forward direction from that same cast transform. Out hit info, we're going to need that. Now we need our max distance. So which is going to be that max cast distance that we have up here in our linear cast serialized fields. And then what else do we need? We need our layer mask. So this is going to be the all collision mask. We're not checking for specific validity just yet. We just want to check all of the basically physical objects in our scene that have colliders. Is there anything else that we need? No, it's just the query thing that we don't need to do. So that will basically give us here, again, just like we're kind of returning here, whether or not there was a hit at all, and then that info on the hit if, again, this was successful. Because we're going to be changing the position count on the line renderer in the projectile cast, I'm going to do that here. So point count equals 2. So line renderer, let's actually go look at the line renderer here. The line renderer component looks like this. This is just a built-in Unity component. It's not part of the XR Interaction Toolkit. It's just like base Unity. Let's actually bring this down right away. Let's do, yeah, 0.33 or something like that. But when we look here, there's positions. So we can say how many positions that we have, and then also they specify kind of where each position is. Keep in mind this is in world space unless you check. Let's turn off shadows while we're here. Unless you check, use world space is checked, so you can deselect that if you wanted to use the local space. But that's not the case for us. So that's what that looks like. We're just setting the position count to 2 because it will always be 2 when we're doing the linear cast, or just the beginning and the end point. And then we can set the line renderer set position. Sorry, 0 is going to be, again, it's starting at that cast transform. And then the endpoint is going to actually depend on, oh, sorry, no, that would be a separate thing. So what is our endpoint? So our endpoint is going to be one of two things. It's either going to be the actual collision. So if this is true, it's going to be the point in which our collision happened. If it's going to be false, then what we need to do is get basically the point at this max distance. And we need to set that point to 2 objects. We need to set that to the position 1 here, as well as our target indicator, which is, sorry, this one here. So let's set the target indicator in one line and then use that to set the position of the line endpoint. So m target indicator dot position is going to equal, and this is where we're going to use our ternary operator, has hit. So if we have hit, that's going to be hit info dot point. And if it isn't, it's going to be m transform dot position plus, so we're starting at the position, but we're going to the m cast transform dot forward, and then since that's a unit vector, that's going to be multiplied by the max distance. And then we can go ahead and use m line renderer set position 1, m cast, oh sorry, that's the m target indicator dot position, because those are the same. So again, if we hit, our position is going to be that point in which we hit. If it's not, we take the position, and then if this is kind of nice to kind of, to wrap in brackets for just visualization. So we start at this point, and then we add the forward unit vector, which is again magnitude of 1, and then we multiply that by the cast distance. So that is basically just max cast distance away from this position in the forward direction. All right, and that is, we can get rid of hit if that default there because we have it being set here, and then we need to return has hit here. And we're gonna be doing something similar in the next video with the projectile cast, but again, there's just a lot more to do with the actual projectile math that we have to do. So anyways, that is done. So we have that value here. So now we have our hit state as either hit or miss, and we might have the hit info. So if this is on missed, this is gonna stay as default. So we want this around so that we know not to read this. All right, so this is altogether like do actual Raycast. Write that comment in there so that, because this is gonna be a pretty chunky update. So what is the next thing that we wanna do is we actually wanna say, hey, if we actually hit something, is this something that we want to actually teleport to? So is this a valid target. In that case, we're gonna start with an if statement and check if hit state. I mean, it should technically hit state dot hit, but for the sake of correctness and accounting for everything, we're gonna do not equal miss, just in case we add something later where there was a detection early or something like that for the valid thing. We have some kind of a shortcut. So we're just gonna make sure that it's not miss in this case. And here we're gonna create basically, because we're doing both the anchor and the free teleport and we have two different masks for these, we're gonna select which mask we need. So again, I'm gonna use another ternary operator here. So I'm gonna create a new layer mask, and that's just the mask that we're gonna use, and that's gonna be what was that called? Not the cast type, the teleport type. Teleport type equals teleport dot free. So if we're doing the free, again, another ternary operator here, this is going to equal the M valid surface mask. And then if it's not, then it's going to be the valid anchor mask. And again, you could put this in an if tree or a switch case if you did end up having more types. Like, I don't know what other kind of type you might want for teleportation, but if there was something else, you could do like an if tree to set this. But now we need to do a bit of something that's a little bit out of the scope of this video for detecting this layer mask. We're gonna do something, do some bit mask checking. If you don't know what that is, don't really worry about it. It's kind of out of the scope of this video. If you are interested, I'll leave a link to an article on bit masking, but for now, just kind of copy this out. We're gonna create a new method here, is layer in mask, just to kind of give you an idea what's kind of going on here. So we're gonna get so we're just going to check if a layer value is in the layer mask. Again, layer mask. And again, just copy this out. Don't worry about it if you don't understand. It's going to be return mask 1 ampersand, not 2. And then another thing, 2 of the less than characters next to each other. 2 closing braces, and then a greater than 0. So for all intents and purposes, what this does is it asks, hey, is this layer valid in this mask? So again, hit state. We're gonna modify this. We already know that it's not miss. So we're gonna ask, is layer in mask? Sorry, this is gonna equal. And that's going to be our hit info. And because we can't get the layer directly, we have to go through transform to then go to the game object to then get the layer number and then the mask that we stored just up above there. And it's going to be, this is a ternary operator. So if the layer is in the mask, that means it is valid. So we're going to do hit state dot valid target. And if it's not, we're going to keep it as a hit because we still want to like do stuff with the result here. All right. So this is now telling us, hey, we either have the anchor point if we're doing the anchor, or it's telling us whether or not the surface is something that we can teleport onto just in general. Next up, if we're checking validity, we can do our angle check. So again, bringing us back to this dot product thing. We're basically wanting to check, again, we have our up vector and we have the normal that comes off of our collision, which is perpendicular to the surface in which it collides from. And we want to check whether or not that value, that resulting dot product, is above the value that we stored earlier, or if it's below, it's not going to be valid. So in the case of this one here, our vector is out this direction, which if we compare it to up and then say we had that same, this value that we have here is the same here, and then we project that onto here, it's going to be below that value. So in this case, this is going to be too steep. So let's actually do that. So now we're checking if hit state is equal to hit state dot valid target, because now we're checking, we don't want to do this extra math if this isn't already a valid target. So in this case, we need to get that dot product value. So float dot value. And And this is going to equal to vector3 dot. And then first one is going to be what we want as sort of our base comparison, which is just going to be vector3 dot up. We're checking on our up value. And then the other one is going to be the hit info dot normal. So again, that's the value that comes perpendicular to the face. And so now we can just check, again, we can do our hit state equals, again, let's just do another ternary with the value being dot value is greater than m max slope. So again, we're doing that stored value, not the one from the serialized thing, because that's just an angle. So we want that. The ternary value, which is going to be hit state valid target versus, it's going to go back to hit. Perfect. All right, so now we've checked and made sure that we have an actual final surface in which we can do. Also, I did just realize this is only if our cast type, not our cast type, m teleport type equals teleport type dot free. So we don't want to do, if we have anchor points, ideally those anchor points will be set up in valid positions anyway. So this is only if we're doing the free teleport. Okay, moving on. Check is valid target. These kind of, yeah, these go together. What are we doing next? Before we actually move stuff, let's change our visuals. So the color that we're going to set this to is either going to be, again, hit state, the value of hit state is going to equal the hit state dot valid. So we're only doing this if the target, or we're setting based on whether or not it's valid. So we're going to have m valid color and then m invalid color. So again, valid target set to the valid color. If it's not, it's going to set it to the invalid color. And then we're basically just going to do, let's just do a set colors color. We'll just do this separately just so that we have it out here. So, and so that's going to include the, so the line render actually has a start color, which we will also set to equal the end color, which we will also set equal to, what is it called? That other object, target indicator. Target indicator, sorry, the renderer specifically color, which is going to equal the color. Color m target, come on. There we go. Oh, sorry, dot material dot color. Okay, all these are going to be set to each other. Let's make it not so long. So I'm just going to drop these down onto new lines here. So these are all just basically going to get set at the same color. So that is now set here. Now we're going to actually apply our movement. This is only going to happen if we're releasing the teleport point. So, and the reason why this is down here and up here is because of all these local variables and stuff. We need this value. So we want to be able to do and detect our release after we've done all of this math. So again, so if we were already aiming and our input axis is now less than the m input trigger value. So in this case, we've released the thumbstick at the point in which we were already aiming. We're gonna set is aiming to false. So that should change this value back to false for future iterations, as well as turn off those visuals that we had there. And then we're gonna do our actual movement here. So if hit state does not equal hit state dot valid target. So whether it is hit, but it's not valid, or whether it's a miss, we don't want to do any of this. So we might as well just return. Again, this is not the type, but the instance. Hit state does not equal hit state dot valid target, return. So we'll get out of here. And then where are we actually going? So vector 3 point. So the point where we're actually going, again, it depends on whether we're doing the anchor or whether we're doing free teleport. So if teleport M. This is a value that we've stored. If our teleport type is teleport type dot free, we're going to want to teleport to wherever just that target point that we hit. So this is going to be hit.target. If it's not, if it's the anchor, we actually want the anchor's center point, in which case, like, you could get this any number of ways. You get it off of a component if you wanted to do something more specific, but in our case, we'll just say the hit info dot transform dot position. So this isn't the position of the resulting raycast hit. This is the position, the actual transform position of the object. And now you might be tempted to say transform dot position equals point. However, there is a small problem, and that is if we actually go back out here, and this is going to compile a little bit for us, what's going to end up happening is, because of the way that our XR rig is set up and the fact that we are going to have this on the actual full XR origin, and we do still want to teleport the whole origin somewhere, but the issue is going to be that when we teleport, it's going to teleport the center of the origin to that point and not where our camera is. Because if the player has moved in the play space at all, they've moved side to side, front, back, at the back of the play space now, the front of the play space now, they're ideally, the way most games are set up anyway, is that you would think that they would want to teleport so that they are now centered on that point. So we're going to need to take the camera's offset into account. And that's why I stored the camera up here, is because we're going to need it. So also, instead of just setting this right here, I'm going to create a set position method. Let's not do that. And that's going to be point. And I'm actually going to create here a public method called set position. Because it would be very handy for, like, if there was something that needed some external component that needed to control where the player was teleporting to, it would be nice to have sort of a public way of doing that. So like, say you had, I don't know, a cinematic where you need to move the player at certain points in like a story cutscene or whatever, you would have access to this publicly. So that's why I'm also making it public. But anyways, we basically need to get the camera's offset. So luckily for us, if we look at, again, the structure of our camera offset, you'll notice that the camera offset here has a Y value, but the X and Z values should never change. So that's handy for us, in which because those don't change, they will change in the camera. So we should have, why is the camera at -10? That's actually pretty crazy. Let's get rid of that. And let's apply that to the prefab. So these values will change. So we can get that, and we can actually ignore the Y value there, because when we're teleporting, we don't need to care about we do want to still teleport, because our XR origin is in the floor. We do still want to do global and pivot. It is in the floor, so we want to move stuff on the floor. Anyways, so back over here. Set position is going to be vector 3 offset. I'm going to create a new vector 3, and that's going to contain camera dot position dot transform dot position dot X. Let's get rid of the transform here. I'm going to actually go up here and store this as a transform, because we don't need the camera. We don't need the actual camera stuff. And we'll store the transform up here. So camera.position.x. And then, because we're just going to be adding this, we're going to use 0 here, and then camera.position.z. And then what we're going to do is we're going to set our transform.position to the point, but we're going to subtract that camera offset, because this represents where the camera is. I'll go back over here. So if our space here, this is our XR rig, this is the center of the XR rig, and let's say this is where the camera is, the value here is this, So if we want to move this, we just basically need to do the opposite to get the center. So that's why we're subtracting. But yeah, so that's that should now be all ready to go with the linear projectile. So let's set up our scene to allow us to use this. So I'm just gonna break this prefab just so that you may not want to do this. You'll just actually probably want to keep the prefab. But in my case, I'm just gonna do this just so that we don't have anything conflicting. So one thing is setting the width of our line. So I'm gonna edit this key and I'm gonna say 0.025. That's a nice clean number. You'll see this is pink. That's because it doesn't have a material. So there is this default line material. If you don't see it, you can just type def and then default line should come up. So that is just an unlit white, but the default line won't really work for us for our target indicator, which I will create a new 3D object, not a cube. Cubes are weird. Let's do a 3D object sphere. We're gonna make this 0.1. And we've just got the default lit here. So I'm gonna create a materials folder, and I'm just gonna create a new, I guess, materials at the top here. And I'm just gonna say unlit. We're gonna change this from lit to universal render pipeline unlit so that we don't have shadows and stuff. And we'll just set that value there. I will set that to 0 just so that it's there. So that's just the object that we're gonna put at the end of our indicator there. So let's set that up with our XR origin here. So we're gonna start with free teleport. We're gonna start with the linear cast type. Our collision mask all, I'm just gonna set to everything for now. You could deactivate stuff. Like for example, actually this sphere, I'm gonna get rid of the collider on it because we don't want to be raycasting to it. Again, you could just put that on a different layer and deactivate that layer in the layer mask, but I don't necessarily wanna worry about that right now. What else actually? Let me just double check. Okay, so let's say for example here, let's create a player layer, and then let's create a ground layer, and then we will create a anchor layer as well. So we'll have those three. So we'll set the entire player here, we'll set that to player, and we'll change the children. The ground here, I'm actually gonna make it bigger. Let's make it 50 by 50. This is going to be on the ground layer. And then we'll do the anchors in a sec. So we've got so setting things up, collision mask, we'll set it to everything for now. We're gonna deactivate player. So you'll see it says mixed now because we've deactivated player. Then we have the valid surface mask. This is going to be nothing, but we will change it to ground. So we can only teleport on ground. I will actually set this guy to ground as well, just so that we have that as like an example. Actually, no, let's set this to default so that it won't be the example, and I'll set something else up. And then we'll have the valid anchor mask will only be anchor. Oh yeah, also valid surface mask. Let's add anchor to that surface, just so that if the anchor is there, we can still teleport on top of it. Maximum slope 45 is fine. The invalid color is red. The valid color is green. That's fine. We need to set up inputs here. Trigger value is fine. The max raycast distance at 10 is fine for me. Let's do the cast transform. So cast transform, I'm right-handed, so I'm just gonna put this on the right hand, and that's just gonna be a new empty game object. I find that a rotation of around 45 degrees is sufficient. So just pointing down in the 45 degree on the X there is perfectly fine for me. And let's rename this to teleport cast we don't have to put transform, it is a transform. And then we'll go back up here, drop that guy in there, and then our target indicator is again that sphere. So let's rename this to teleport indicator. That's fine. So last thing that we need there is just our input. So I'm going to go ahead. I'm going to go through this very quickly. If you want more in depth on how to use the input system, again, there's a video linked in the description there for that. But I'm going to create a input. At the bottom, input actions. My input actions. We're going to go ahead and create just a default action map. Have our call it move, and that's going to be set to, that is a button. No, it's not a button. It is a value, and it's going to be a vector 2, and that will be a not usages, XR controller, right hand, usages, primary 2D axis, and that's just going to be that's our thumbstick. So that's fine. Yes, we want to save that. Do we have the input action manager? Sure. That's already set up for us from OpenXR, which is really nice. Otherwise I'd have to create it myself, and then we'll just put that in there. That should automatically activate and deactivate that for us. And with that, we should be ready to go. So let's go ahead and jump into the editor and check this out. So there are actually a couple fixes that we need to do before we hop in. We created the action and we set it to kind of start up the action map, but we need the to actually assign this in the inspector here. So go ahead and do that. The other thing is that there is a problem with our teleportation because this is supposed to be local position, not the global position. Again, we're trying to get the offset from the center of the XR rig to our camera, so the local position will give us that, whereas the global position is offset based on the center of the world, which is definitely not what we want there. And then last but not least, I want to put in something here for testing our slopes. So I'm going to go ahead and create another cube. I'm going to make it like, I don't know, 10. I don't know. What's that? 1, 10? No, 10's too big. Let's make it 5. Zoom out here. And then I'm going to rotate this about 30 degrees. Move it over this way. And then let's set this to global and then just move it down into the floor. So basically what this is going to do, as long as we set the layer here to ground, is this side is 30 degrees and this side is 60 degrees. And since we set our max free slope angle to 45 degrees, this side should be valid, this side should not be valid. So let's go ahead, jump into the headset finally, and actually test this thing. All right, headset is on. Let's go ahead and hit play in the editor. And we've got hands that are moving and tracking. We've got our slope, we've got our box. If I press the forward stick, we have a line that is green because this is our ground. If I point up to the sky, that's our miss because we're not hitting anything. That's just the sky, and that's the maximum distance there. Now this guy here, this is our cube, which is set to default, not ground. So even if I'm on the top of the box, it is still invalid. I can teleport to each of these points. I can go over here and let's test the slope. So 30 degrees is perfectly fine. We can teleport onto that. If I come down here, try the 60 degrees, it is invalid because that's too much a slope, even though the whole object is a even though the whole object is on the ground layer. All right, let's set up some anchor points. You could do a whole setup with like doing special transition effects and stuff like that, but just to sort of make this as easy as possible, I'm gonna go ahead and just use the layer that we set up before. So if we have a 3D object, I'm gonna go use a quad. So I'll call it teleport anchor. Create a new material here. I'm going to just create a normal material, call it red, and make it red, and set that to our anchor point there. We'll rotate this. It's back to local. Rotate this and move it just up ever so slightly. Move it along here so that it's away from our start position, and then we'll duplicate it, put it over here, duplicate it, put it over here, and that way we have a few anchor points that we can sort of, let's actually move this one back here, a few anchor points we can kind of play with. And then all three of these, I'll select all three and set them to the anchor layer. So now if we go over to our origin, set this from free to anchor, and make sure, yeah, valid anchor mask is set to anchor. Now we should be able to only teleport to those anchor points, and we should be centered in those anchor points. So let's hop back in the headset and try that out. All right, back in the scene. Sorry if I turn away here, actually. we don't have turning enabled. We don't have a turning component yet, so maybe that's something that we'll do in the future. But we have these teleport anchor points now. So you'll see now the ground is no longer valid. But if I go over here and I hit the teleportation point, and just to make it clear, I'm going to hit the very corner of it, and we teleport to the center of the teleport anchor. So I can go to any of these. Again, slope doesn't matter. I mean, these aren't on a slope, but also this is set to ground, so this doesn't count. But I'll also show you that you can also be off center. So I'm actually going to move all the way back in my play space here, to the point where my boundary is just starting to show me the rest of the room. And if I now click here and teleport there, you'll see I am centered in the play space again. So if I go back to center, you see I'm standing over here, and then so it's that offset is working correctly, and that is the same math for the free teleport as well. So we know that that's working. And with that working, that pretty much wraps up this video. Again, if you want the projectile raycast, that's going to be another video. I'll have that linked. We're basically just going to fill in those couple functions that we set up there, so that we'll be able to just basically use this same system, but with the projectile line. If you do want to support this channel, I do have a game out on Steam and MetaQuest. It's called Neon Cipher. It's a puzzle platformer. You can go ahead and pick that up if you so desire. Otherwise, like and subscribe. Got more tutorials coming, as well as maybe some devlogs on the new project I'm working on. We're still in pre-production right now, so there's not a ton to show, but there's been some shorts that I've put out that have sort of gone over some of the prototyping stuff that we've been doing. So if you want to see all that, make sure you hit subscribe. And with that being said, I'll leave you guys to it. Have fun making games.